All right. I want to say thank you, everyone, for coming here tonight. And I know some of you may have driven very far, so thank you. My name is Mike Jadoo, and I'll be your presenter for tonight. And I want to say a special thank you to Bethesda Data Science for hosting me, and also looking forward to the new name. All right. So today we're going to be talking about machine learning, specifically classification model. So I got a little cough going on here, but please bear with me. The agenda for today, so I'm going to be talking about machine learning and deep learning as well. And then I'm going to go more into supervised machine learning, the classification model. I'm going to talk about some use cases. And I know that Itai had mentioned some of the things that AI is kind of like embedded in our daily lives. And I'm also going to show you some more cases that's the situation. Then I'm going to talk a little bit about R. Then I'm going to talk about our case study for today. It's the credit card data set. We're going to be doing some fraud determination. And then we're going to go into neural networks. So we're going to run a neural network and to see how that compares with our machine learning model, classification model. Okay. So a little bit about machine learning. So machine learning is a branch of artificial intelligence. And this is the science where we focus on data and algorithms to imitate the way that humans learn. And also it aims to gradually improve accuracy. And today I'm going to be covering only two, or just mentioning two types of machine learning here. But there's four, but I've also heard there's 5 different types of machine learning techniques that are out there. And I'm not going to go into that. So we have supervised learning, which is clustering. So this is the situation where it's unlabeled data, and we're creating a model, but we're not training the data to discover or to perform analysis. But we are just using the unlabeled data to find patterns within the data structure. Next, we have the supervised learning. We have regression modeling and classification. And so for regression modeling is mostly for prediction of continuous variables or data points. Classification is more for like different classes. All right, so with the classification model, we have 2 different types. We have the binary classification model, and then we also have multinomial classification model. So with the binary classification model, these are situations where you're looking at different classes, maybe men, women, or could be they have COVID or not. That's another situation, binary. Also used in fraud detection. Multinomial classification model, this is a situation where we have multiple different classes that we're trying to predict or get the probability of, right? And so again, with the supervised learning, the big difference between that and unsupervised is that in supervised learning, we're training the model, right, to help us come up with our predictions and also figure out our probabilities here. Okay, so different cases when classification is used. So we have document classification. So actually, there's a new method that has recently started coming out, but some of you may have heard about it. Whereas people are using machine learning classification models to accurately correct VA health checks, where veterans are making a claim for their medical benefits. They typically get like a particular score. Now they're using, for some veterans who are making the claim that their score is incorrect or their classification is incorrect with their medical benefits, now they have professionals who are actually using machine learning models, classification models, to fix this situation. And that's, so a lot of people are getting their VA medical benefits corrected using this method. Next is spam filtering. So with spam filtering, this is something you would see in our emails, if it's a spam or if it's not spam. So we have an algorithm to determine that. Right? We train the model, then we come up with our predictions for these different classes. Next, we have medical diagnostic tests. So this is something that's similar to like COVID, where during the pandemic, we had machine learning models were implemented to efficiently predict whether a person had COVID or not. Right. Researchers can also use machine learning models to predict new diseases that are most likely to emerge in the future. Then there's fraud detection. Right, so with fraud detection, it's maybe framed as a problem, whereas 0 is not fraudulent, and 1 suggests it is a fraudulent type of activity that's happening. And so we're using, and I'll talk about the data set later. So these are the different cases for popular cases where classification models, machine learning classification models are being used today. Does anyone else know of like any kind of other scenarios that could be used today for machine learning classification models?
Yeah.
Yes.
I've got a question.
Yeah.
I know they can take CT scans, images,
Right.
in medicine for pancreatic cancer and can help detect when one is abnormal and route it to the radiologist to say, hey, this is flagged for high risk for a pancreatic cancer scan. Can you talk to us just a tad about images as opposed to, you know, the binary system and large language models?
Not really, not here today. I mean, I wasn't trained in as far as like image. Okay.
Oh, yeah, let's talk later.
Okay, but I'm assuming that there's some sort of module that reads in these image files and creates some sort of maybe you've worked on that data, right? Maybe it's no, you haven't.
Imaging, it's all external evidence. Yeah, we're talking about.
Okay. Okay. All right.
I did it too at NIH.
Oh, great, yeah. Please, don't come talk, or anybody else who has knowledge of this, please come talk to me. I'm putting together a program.
Okay, great. All right. Anyone else might have known any other cases where machine learning classification models might be used? Binary case?
No, I'm not sure if it is. I was about to say the product recommendation on, say, Amazon, but I don't think it is.
Oh, okay.
Yeah, recommender systems, they're also AI. And they
Oh, they are AI, but are they classification systems?
They use different algorithms, but
Okay.
not so much like this.
Okay, yeah, never mind. Sorry about that.
Yes.
Indication detection. So as pharmaceutical companies have different indications that the drug can be prescribed to, you
Oh.
normally see the actual longitudinal prescription history of the patient, but based on, they don't know what this is being prescribed for. They just have the longitudinal prescription history. You can decide what disease that patient has based on the history of the drugs that they're taking.
Right.
That way they can see that my drug is being used more for this indication rather than this indication. And that's a binary classification.
Nice. Thank you for sharing that.
A different use case is going on in the National Institutes of Aging, and they're trying to, I'll give you an example. Parents who live at home, you're worried about them falling and not being able to, you know, reach help, and they don't want to wear the button around their neck, right? They've got shoes that will detect where somebody is falling and alert.
This has a fall detection. Fall is IoT devices, so fall detection.
And yeah, there's AI in that.
All right. Well, thank you all for sharing that, and I'm sure we'll talk some more later after today. All right. So next, I want to talk about the data science process and R. Right. So data science process. This is pretty much the lifestyle of when we're performing some sort of model creation analysis. First, we typically going to collect the data, and that could be either from external sources or stored in a database, right? And then we're performing some sort of ETLing process, transforming and then loading it. And then we're also cleaning the data, checking for missing observations, because obviously the missing observations has some cause our analysis to be biased. And we're going to go into afterwards After we clean the data, make sure it's in the proper format, we're going to go into exploring the data. So this is more of the exploratory data analysis, where we're performing some visuals. We want to check for outliers. Outliers in our data could also cause some biases. We may want to look at our data to consider what else is happening in our data set, and we want to check all the variables. Then we want to go into modeling. So there's different types of models that are out there. I'm focused on one today. There's several that are out there, regression, k-means, those different things. And then after that, there is deployment. Right? And we deploy our model to whatever case that we want to use it for. And then we could do all that using R. Right? So R, it's not just a letter, it's a lifestyle. Right? That's right. So R supports, extensively supports all the processes within the data science lifecycle here. It's used extensively in different places, great for visuals, and I'm using that today. Yes?
Sorry, good question. What R stands for?
Oh, R, the programming language.
You know, there was like Ada and then...
No, it's just a letter.
See, like
Back
R.
in the day, they made a program called
S, right.
for statistics, and then the guys in New Zealand, they just kind of open sourced it, and they were like, well, that's what we picked. I don't know if there's a story behind that.
There's the next in evolution, and so after that can be Q.
I think I'm going to stay with R for a while. Yes, sir.
So R is open source
R is open source, yes.
machine learning.
Oh, there's a mic here.
So R is basically an open source machine learning language?
No, well, R can be used for machine learning.
Okay.
But R is an open source statistical programming language. But it's used for machine learning. But you can also use Python as well, but today using R. But we all have our favorites. Yeah.
What are the main differences between Python and R? Could you summarize that, or you want to?
Yeah, so quickly I can. So with R, you would, 1 second. With R, you would typically get the more advanced statistical algorithms that developers are putting out sooner compared to Python. R typically has their graphics a little bit better compared to Python, but some will argue that. Okay, all right. But Python, it's been tested to be faster compared to R. Python has been known to be used more in industry and a lot of different places. And we see Python in Esri, their products, and also other applications as well.
It's Python's an object-oriented language, whereas R, I think, is a functional language.
R is a functional language, but it does have some features of object-oriented. Yeah. Thank you. Does that answer your question? Okay, so let's get into our story for today, and we're going to be looking at the credit card data set. So those of you who are planning to follow along, in the GitHub, it doesn't actually have the data set, but I would recommend to go to Kaggle to pull that data set because it's quite large. And it couldn't fit in my GitHub link. So the credit card data set, this is for fraud detection. So it comprises of transactions that the European credit and credit card holders made in September 2013. So the data set shows transactions that occurs in 2 days. Right? So that's the data set. And there were about 492 frauds out of 284,807 transactions. So, and the data set is highly unbalanced, right? And the positive class, which is fraudulent accounts, account for only 0.172% of all transactions. And so the data set has been collected and analyzed during a research collaboration between Worldline and the machine learning group over in Europe somewhere. And so this is used a lot for educating and also training for fraud detection. So it has about 30 variables. You have the class variable that we're going to be using for in our model. Well, we're going to use all the variables in our model. We have time and also amount variable. And then we have V1 through V24, I believe. Yeah, no, 28. So the V variables, these are numeric inputs that have been transformed using principal component analysis so that it could hide people's particular information. So this is for data privacy issue. But they want to make this data set public so people can use it to learn off of. Right?
Do you know what the PCA was done from? What was the vector that was used to do the PCA extraction?
Oh, that was different. Different trends. I believe there's different transactions from customers, I believe. Yeah, V1 through 28, I believe, yeah. Any other questions? Okay. All right, so we're going to talk a little bit more about the classification. So here, we're doing the binary example. So when and I'll be able to show some of the R code that I have prepared for us today. So when we're starting our process of creating the model, first, of course, we want to check our data, and then we want to check for missing information, do some exploratory data analysis, and checking our different variables, do some visuals, and then we want to start working on creating our model. And when we're creating our model, we want to first start off with training the data, which is doing cross-validation. So when we're doing cross-validation, there are several different options. So there's a reason for this. This helps to alleviate the case of overfitting. With cross-validation, there's several different techniques. You have the random split. You also have the k-folds. And you also have other types of methods. But today, just going to do the random split, which is pretty much everyone knows this, the 80-20. So we have 80% of the data is going to go to the training data set, and then 20% of the data is going to go to the test data set. So we're going to train the model first, and then after we train the model, then we're going to go into the testing to using the test data set to get our evaluation metrics that we're going to use to evaluate our model or models.
Is the data just an individual? Every row is an individual. It's an individual. It's that individual isn't duplicated across the rows.
Right.
I thought these are transactions from 2 days, right?
Yes.
So it could be the same individual.
It could be. I'll have to check more into that.
That will definitely impact the way you decide to do your test transport.
Right.
Individual. You might don't want to have the same individual with two different.
Right. You might want to go with the k-folds. Right.
Yeah, like a stratified split.
Yeah. Okay. Right. Yeah. So usually 80% of the data goes to training, 20%. So this is the 80-20 split is usually driven by the Pareto principle, and which states that 80% effect is driven by 20% of the causes. Just want to put that up. Okay. So we have here just some assumptions here. Of course, just like in the linear regression model, we have our assumptions that we need to follow with our modeling and checking our data and making sure the data can go through our model pretty smoothly. Here, the same thing with classification models. So I just have two simple rules here, going off of where there's minimal no multicollinearity among independent variables, and observations are to be independent of each other. And so when we create our model, and I'm going to show the R code, we're going to go through this. We are at the end, when we're creating a model or models, we want to use different statistical measures to grade how our model is performing. And so I have here just a few. I have a confusion matrix. This is for classification models. And also confusion matrix, accuracy, and there's also several others. So when you're predicting using regression, machine learning, you're going to have different types of model evaluation measures. So typically, you're going to have like the R squared, or also the RSME, root mean squared error, to evaluate. Well, you could just use those to evaluate your model. But here, we're not doing that. We're using these different measures here, Because before we're predicting with regression, here we're working with classes, right? And so with the confusion matrix, here we use it to describe the performance of the classification model. The accuracy, this is simply a measure of how the classification model correctly predicts. And then we have the ROC, AUC, and this is, I believe it's like under the curve. This score shows how well the classifier distinguishes positive and negative classes. It could also take values from 0 to 1. And, okay, so I'm going to go ahead and go into your code. So I didn't go over all the model evaluation measures for a classification model. So obviously, wherever you're working or for your project, it's up to your discretion to figure out which ones you want to go with, right? But at least have like a few, like 4. Accuracy or confusion matrix, definitely want to be one of those for your for whatever efforts you're using. Okay, so here I have in R. I'm just here at the top showing the different libraries that I'm using. I'm using cat tools to help me with splitting the data. We have these other different types of packages here, LARS, CVMS, Yardstick, to help us with creating our models and also to do some visuals. We also have ggplot2 to help with that. And also we have the caret and tidy models. So here, this figure, this fig object, this is this is a function that I'm going to use later for an output that I want to show you. And so you don't need to worry about that. But when you look at the code, you start exploring about what's there for you to try out, and maybe you want to take it and use it. So first, we're going to pull in our data. The data is really large. I'm not going to run this block here or this chunk. So we're going to go ahead and make sure that our class variable is a factor. Right? Factors are 1 or 0. Right? Then we're going to go ahead and I check it here, and it's a factor. Right? So I was checking our data, checking our data structure. So then we're going to start doing our exploratory. Exploring our data. We're going to check our structure, the summary. So we're just checking here what our data comprised of. And then here we have our summary for each of our variables that we have. So we have our measure of central tendency, minimum, maximum, and quartiles. For all of our variables. And here's just a count of the class variable here. So going down, so I want to make an image, some visualization here about our class variable and look at its distribution. And we can see that this data set, it has a lot of that is not fraudulent. And then we have a little bit here that's fraudulent. So, I mean, just different visuals. I mean, depending on how you want to perform your analysis or who you're presenting it to, you may want to choose different types of charts or graphs. But I'm just showing some basics here. Here I'm showing some distribution across time for our class variable. For 0 and 1. So we're just still in the exploratory data analysis here part. And then here, these are some quick, some really nice snippets of code that can help us count our missing observations. So remember, if we have missing observations in our data set, we try to run it through our model, it's going to cause problems. Right? Either it tanks or it's going to cause us some bias estimates. So we're going to check for that, and we see we don't have anything. Count 0 totally, and so this first one is counting for the entire data set. Here it is counting all the columns in our data set to see if it has, this is a count of missing observations. So we, hey, it's pretty much clean. Right? Nice. So we're going to go ahead and start with creating our model. We're going to do our split here. And from that, we could also do some more analysis as well, some more charts from that split. So next, we're going to use this recipe function here. So this is prepping our data for pre-processing for a classification model. So this is I believe this is coming from the tidy models. And we're setting everything up, and then we go ahead and define the logistic regression model, and we're putting all this here together, create our workflow. And down over here, we're training our data at this point over here. Anyways, at this section here. So we train our data, and we store it into the log_fit object. And we continue down, and we use the test. We go into here, and we do the predict, and now we're going into our test data. And so after we do that, we want to go ahead and collect our measures. So first I want to start off with the confusion matrix. So I made a visual of that so that it could be really clear. And so we have, with the confusion matrix, we have different types of variables that's in there, or these different boxes are defined specifically. So we have true positives, where we predict the positive is true. And we have true negatives, where we predict negative and it's true. And we have false positives, where we predict the positive and it's false. And then we have the false negatives, where we predict the negative and it's false. So that's with the confusion matrix.
Just scroll down just one little bit
Yeah,
more
sure.
so we can see the bottom label. Just what was it at the top?
At the top, sorry. Yeah.
Okay, I see.
So this is what we predicted, and this is our regular data. Yeah.
So top left is true positive.
Yeah. And next we have, we're calculating accuracy in these other measures. So with accuracy, that is we're determining the percentage of how often our classifiers correctly predicts. And then we have also precision. So this explains how many of our correctly predicted cases actually turn out to be positive. And then we also have our recall. And so a lot of that is just right over here. So recall explains how many of the actual positive cases we're able to predict correctly with our model. But here, we can just collect it all, and we have all of our output right there for us. So eventually, and you could obviously create some R functions to collect this information here and put it into print statements to give yourself a nice table, but I wasn't able to do that in time for tonight. So, and then you have the F-score. Yes?
So I imagine, just from the looks of it, you analyze all the transactions in
Yes.
your data set.
Like 80%.
No, we trained the model, and then we used the test data set afterwards to get to, and after when we used our test data set to come up with our evaluation measures. And those evaluation measures that we have, this is what we use to grade our particular model compared to other models that we possibly want to try out. I mean, we may want to add some variables, may want to take away. It depends. We may want to do some transformations as well.
Where does the weight come in to compare what you have to your I guess, expectation?
The weight.
Got to your
In the end, you have balanced accuracy, like 82%.
82%.
Right now, yes.
Now, when you're saying the word weight, how are you using that? Like, what context are you using that?
I guess you predicted that there's X amount of fraudulent transactions.
Right, yes.
Out of the whole data set.
Yes.
So.
Whether fraudulent or not fraudulent?
Fraudulent compared to not fraudulent.
Yes.
Perfect. So you predicted X amount of fraudulent. You're off by this much. How are you going to close the gap to where if you were to analyze a different data set 2 days, a month after, to get closer to?
Well, if you're using the same variables, you'd use these different evaluation measures and compare them and to see how it measures up. And that's how you can check.
Okay, so
If you notice your model is under-predicting or over-predicting positives, you can modify the threshold, and that's called calibration. And to visualize it, you can use a calibration curve to see whether it's under-predicting and over-predicting positives, and then adjust that threshold to get it to what you think is right.
And obviously, like in a more complex setting, you would tune it for holidays because there might be more fraud during a certain season.
Right. Yeah. So there is some tuning that happens in here, and there's something I just forgot, and I'll get your question here in a second. So I did do some scaling for this data because again, the V1 to V28, those were it underwent the PCA transformation. And obviously that has some volatility in it, so it had to, it's scaled in one of these steps up over here, which is something I didn't mention. Yeah, so we went through some log scaling here. So I was done over here. Sorry. And yeah, so there is some scaling that is involved in this. Yes.
Can I ask, you sort of glided by, like, I think it was on line 156 maybe, where you said you did the training. Was that just a function call, or?
Yes. So I set up a work. Oh, go ahead.
Yeah, so could you explain what that call does, and what the parameters are, and are there any like optional parameters that weren't specified there that you could include?
Right. So here I'm using these particular sets of functions to just create like a sort of a workflow. And so here we have the GLM. So I'm giving this, setting it as, this is here setting engine. So this is like a generalized linear model. So this is a type of function that allows you to do different types of linear models, right? And here we're identifying that here as classification. That's what we're doing. And that's, oh yeah, so that's what we're doing here. And then we're storing it into this object here, whereas we're going on down over here, we're adding this here, and we're adding the credit recipe here, which was earlier here.
Mike,
yes, for
could you
pre-processing.
show everyone how you would bring up the documentation in the help window? I think the shortcut is like F1. If you have your cursor or caret on the function, you press. I think it's F1 or function F1, something like that. And then it should bring up in the help pane in the bottom right. It should bring up the info on that particular function.
Oh, function F1 is not working.
You can search for it.
Yeah,
Yeah, that's another option. You can just, in that little search bar, you can type in whatever the function name is.
Well, yeah, just put on one of the functions and hit F1.
In the console, you can put in question.
Yeah. And yeah, it'll explain. And so basically, all these functions, they're from like the hiding models.
Yes, the hiding models.
Group of packages, and they're going to have different pieces. And so like set engine sets the backend for running, and you can use a different backend, but there's no reason to for it. Like logistic regression, you can just use GLM, which is kind of the basic thing you would do in R, but it's in like a standard flow of our programming language because you're using this hiding models framework. So you can swap out the backends without changing the code. You just change the arguments you pass to the functions.
So it's almost like having a template.
Right.
Yeah, it's like that.
Yep. I would have to talk with you later afterwards. This is taking up some time.
Sure.
Okay. All right. Okay. So get that over here. We create our measures. We also have our F1 score. That's another measure that we can use to grade our model. And then, yeah, so we have another type of visual or measure. We have the AUC, or the rock AUC. It's the area on the curve. And we could also display that as well. And so, and this is what we got right over here. And so I want to go back to the presentation and show us what I collected. All right, so we have our confusion matrix on what you see on your far left, and we have the different. So I have here listed the different percentages. I found the different percentages be more useful than the counts, but oftentimes I have the counts there. And then we have our evaluation measures. We have our accuracy, recall, precision, and everything here is pretty much graded. So we have, it looks to be okay, right? This is a classification model. We have some concerns here, and recall, and also the F score, but it looks okay. Yes?
Is the true positive or true negative, can we switch around?
What?
Yeah, just because the labels. I think
Yeah, the labels, the output was giving me some issues with.
Oh, okay.
Yeah, so I have to switch it back and forth. Yes?
Go down the scores as opposed to the evaluation and give benchmarks where could you please go down the evaluation versus the scores and give a benchmark for what would be an acceptable value and what might be falling out of range and need attention? For instance, you said recall at 0.64 might be a little out of range. I don't have a good sense of where the baseline should be.
Oh, that's good. Well, I mean, if we want to have an accurate model, we want to have it in the high percentages. So these are just more like in percentages. So probably like 0.9%. I mean 0.90. Right. So that's what we want to high. But if it's like lower, going to like the 0.5, I mean, we may have some might be concerns right over there. For recall, yeah. So for the recall measure. Yeah, this number defines true positive divided by total number of actual positives. So this explains how many of the actual positive cases were able to be predicted correctly with our model. All right, so that's what the recall measure does. So we have 0.64. We may want to consider having a higher number than that.
A little better than flipping a coin. That's what it's all.
Yeah.
What I'm seeing there is accuracy is 90%.
No,
Recall is 64%.
Yeah, so say I have 100 data points. Sure. And I train a model off of 99 of them being yes and one of them being no. And so I predict no 100% of the time. I will still get 99% of the time correct.
Is it 90 or 99? It's 90.
It doesn't matter. So I'm just saying that if I make a model that says no all the time, then I'm going to be right 99% of the time.
Agree.
So that's why you look at the recall, and it's pretty bad.
What does recall means? I don't understand that.
About the total truths that they were right, you predicted 64% of those correctly.
So again, it explains how many actual positive cases were able to be predicted correctly with our model.
So it's true positives divided by true positives plus false positives?
Yes, or false negatives.
False negatives.
Yeah. And so that's, yeah, so this is what I got from this particular instance of running this model. Obviously, if it's not to our satisfaction, we want to either consider fine-tuning the model, maybe add some more variables, and then rerun everything again. And also check, and if these are the measures that you're going to be using to evaluate your model, to collect this information here again, and then start doing some comparing and do some fine-tuning afterwards. Yes?
The number below The percentages, is that the number of transactions or is that something else? Like,
Oh, this is something else.
this says 99.8%. What does the 64,191 represent?
Oh, these are the counts.
Those are the counts.
Yes.
Okay, so it doesn't seem like that recall is accurate then. Because there's no way you would be down to 0.64. I mean, if those are true positives, 64,000.
Oh, this is the counts from the predicted.
I think it's like false positive divided by true negative or something like that. There is a formula. Basically, there is a formula.
Right, I mean, it just seems like this was relatively very accurate and you would never get recall that low, but if that matches what we're seeing in the chart. But I'm just
No, I mean 0.64 is like 40 divided by 70 or something like that.
Yeah.
What I mean is like there are formulas and it's correct.
Yeah, I understand that. I'm just saying intuitively, or just looking at the numbers, it doesn't, but we don't really have to.
Yeah. We could talk more
Maybe
after.
I was looking at the numbers wrong,
Yep.
and there might be a simple answer.
It's not, you just, the labels are flipped, but.
Yeah.
So what you're seeing is true positives, false negatives.
True positives is the
The
bottom right.
labels were just.
Oh, maybe that's
Yeah.
Okay, so so I just created the machine learning classification model. I showed a lot of the different steps that you can go through, but the important one is we're pulling in our data, we're cleaning it, we're doing some EDA, exploratory data analysis, checking our information. If we're considering transforming our data, do some logarithmic functions, we want to do that. And then we go ahead and do our cross-validation. In this case, we're doing the random split, 80-20. Other cases could be something else, I mean k-folds or anything else like that. And then go ahead and train our model, and then we go run our predicted from our training, put that through our test data set, and then we collect our evaluation measures, and then we have the information that we want to use to grade our model for machine learning. Okay, so next I want to go into deep learning, also neural networks. So here for tonight, I'm comparing what I just did with the machine learning classification model to a neural network model that I'm going to go into here. So with neural networks, this is a network or a subset of machine learning which is inspired by the human brain, our neurons. Right? So this, they mimic how biological neurons communicate with one another to come up with a decision. So neural network consists of a couple different features. You have the input layer, which is on the far left of the diagram, I think. Yeah, here we go. So we have our input layer. This is pretty much our input variables. And then we have our hidden layers. So our hidden layers, this is pretty much the neurons or the transformations that take place during when we're running our model. And then we have our output layer. So the first layer, we receive our raw input, which is all of our variables, which is, in our case, it would be class, amount, time, and V1 through V28. And it's processed multiple times within our hidden layers. And this is what this section is doing here. And I'll talk about these different features here in a second. Yes?
So, are there any situations where they might use multiple input or output layers?
Yes, you would have multiple input layers. I mean, the input layers would be your variables.
Okay.
So that would be input variables. Output layers usually one, or it could be two. Or actually, it could be a couple. Yes?
It looks like you have two neurons and one input layer.
Oh, that's just for just describing what neural networks is.
In that case, why would you need multiple input layers for multiple variables? You could just put more neurons in the one input layer.
Well, this is just showing just this is just showing the models. I'm not really like using this as a case.
I can give a scenario.
Yeah.
If you're mixing data types and the two input layers are completely different, then they can merge further down in there. But if you're doing something like image classification or anything like that, where it's a single data type, it can all flow into the same way.
Okay, so I wasn't understanding your question. Sorry about that. Okay. So here, I'll talk about some additional features. So yeah, we have our hidden layers, and then we have these different arrows, and we have our circle. Well, our circle's a neuron, but going over here, just a little bit more of a focus, and I think. So we have within neural networks, within the hidden, well, actually from throughout the whole neural networks, we have different features. We have our weights and we have our biases. We also have an activation function. So with our weights, so these weights are added. So we have each of these neurons have a particular value, and as it goes through the process of the model, the neural network model, we have different weights. Then these weights are added on to particular values from the neurons. But then we also have biases. So biases, they take away values. They take away from the value of a particular for a particular model. And then and each of throughout the neural network, we have these different activation functions where we have calculations that are done, which transforms the information throughout our model. And so that's what some of the main features that we see that we have here. So that was a very high-level explanation of that. Okay. Right. So with neural networks. They're really good at handling unstructured data. So models trained on structured data can easily learn from unstructured data, which reduces time, resources, and standardized data set. Neural networks can handle large data. It's also, neural networks have a high accuracy. And also, it's really good at pattern recognition, neural networks. Okay. And so we're going to go ahead and use our neural network on the credit card data set so that we could, just compare what's happening. So in the code I'm about to show through the here in a second, we have our slide. I'm going to be using the neural net package from R, but there's other packages that are out there that are obviously better. There's, I believe there's TensorFlow and there's some Keras. Keras, okay. So Keras, but I'm just using neural nets. I'm just showing a simple example. And yeah, so you can do it at, for your own project as well. So here, we're at the very top. I'm showing that we're doing our split. We're splitting our data. Yes?
Yeah, so one small one and one thing, the fourth line in the code that's already being corrected in the recall, but there should be a minus in front of the seconds.
Over here?
Because that's basically taking the complement of the training set.
Where?
On the test, credit card dot test, which would be minus split.
Yeah.
Oh.
Yeah, that's why the space is there.
Oh, okay.
You can draw it on the monitor with the Sharpie.
Yeah. Okay. Well, thanks for pointing that out. Yeah. So we have that. Yeah. So we have. Yeah. So we're splitting our data, and then we're going to go ahead and just doing some scaling from what I shared before, because this the variables v1 through v28. It undergoes some sort of transformation, and it's because those variables to be highly volatile. So we're going to do some scaling so that we could put it through our model, and we could have somewhat of accurate predictions. And then down over here at the bottom, this is the actual neural net function that you would use to do the neural networking model. And some of the parameters here, so we have our class variable, that's our variable of interest, and then the squiggly line here, and then this dot indicates we're just going to use all the variables as the independent variables for our model. Next, we're going to be pulling in that particular data set that we're using. We're using a trainer data set, and then we're going to set the parameters for our hidden layer. So here we're going to put 5 nodes initially, and we're going to have 2 layers within our model. And then we're going to have linear output is just false. So that's classification. Yes.
I know you didn't set a seed here. Is that necessary to set a seed? Sorry. Is it necessary to set a seed?
Yes.
Okay.
Yeah, I didn't put it here. Sorry.
Okay.
Yeah, and then next, we go ahead and plot our model that we had done, and then afterwards, we'll take that information. Down over here, and then we're going to create our evaluation measures from our predictive values using the test data set that we had from before. So yeah, down over here, we're doing our scaling again. This is for scaling the test data, and then we're just going to go ahead and after we trained it, now we're going to the test, using the test data to get our predicted values, so we could use that to create our evaluation measures. And I think I just skipped ahead. How are we doing on time? Good? Okay. Oh, all right. Okay, so I'll show you the code afterwards. But so here, after running the model for neural networks, are using the same data set, we came up with evaluation measures that shows it to have a better performance compared to the machine learning model. And so we see here the accuracy is at 0.99, our recall is at 0.99, and precision. Our ROC, AUC went down a little bit, but F1 score is 0.91. And yeah, so we do see improvement there in our evaluation measures. Yes?
What does F1 score mean?
So F1, that is...
The harmonic mean of recall and
yeah,
precision.
the recall and precision.
Combines the 2 scores into 1.
Oh, okay.
Yeah.
Harmonic.
Yes?
The scores change with the data set changes in terms of volume? Like, are those related?
Possibly. When you say the word volume, are you suggesting more data?
Exactly.
Possibly, yeah. Yeah. But again, we're comparing the same data set. So if you're getting more data, then you want to compare apple to apple. So the machine learning model, you want to do use that new data set with the more observations on that model, get the grading criteria, and then do it again for the neural network model. Okay. So have a fair comparison. Yeah. So yeah, just comparing the two. Yeah, the output's kind of strange. So in R, there's lots of different functions or packages that'll give you some really nice displays for your classification models, and you want to pick one that's really good. I happen to pick one that was kind of flips around all the time, but that's okay. But there's some really nice ones out there, so I would recommend for you to explore that. But yeah, so here I'm just comparing the two, classification model and neural networks. This is a confusion matrix. And here I'm just showing our evaluation measures, pretty much comparing what we did with the machine learning model, classification, and our neural networks model. And the neural networks model that I ran, it wasn't complicated. It was just set some parameters, just make a decision on how many hidden layers I wanted to go with. But there's also other types of features that you want to consider when you're working with neural networks. For example, RePOC, iterations. So that's something that you would need to consider when running your model. It may take some trial and error for you to figure that out. But yes, it's not it's not difficult. It's just something that could be considered when you're looking at different problems too. Yeah, especially with like fraud detection or anything similar. Yes.
How did you determine how many enablers to use in your neural network? Was it just an arbitrary choice?
For me, I went with 2 layers and 5 nodes. It was initially an arbitrary choice, but there is a way to figure out how to systematically initially pick the right ones to go with first. But keep in mind, when you're running your neural network model, this model is going to take a long time to run. So it's not going to be like how we had our experience in the machine learning model, where it didn't take too much time, maybe a minute. Neural networks is going to take a couple minutes, 5 minutes, maybe longer, depending on the size of your data and how complicated you're setting up your model to be. So also keep that in mind as well, the time, because neural network model does take time for it to run. Does that help? Does that answer your question? Okay. Did you have a question?
I can ask it later.
Okay.
Besides the speed, is there any reason to choose the first model? The neural network?
So it could be depending on your use case, or maybe it's you're working for a customer or a particular firm, and you're having to run different models, and you're running a neural network model, and you're having to decide whether to use, let's say, a machine learning classification model or neural network, and maybe it's simpler to explain the machine learning model compared to neural networks. But that's going to, again, depend on how accurate your model is. So you'll obviously want to go with the best model. So it depends.
I mean, is it always the most accurate model?
Neural networks would be, yeah. Not always? Okay. Yeah.
I think another reason you might want to use logistic is like interpretability of the coefficients. If that's something that a customer is really like very concerned about, like if this variable goes up by a certain amount, what are the log odds or odds of, you know, a fraudulent transaction occurring? So I work with like GFR in kidney disease with children, and we were using neural networks, and when we were comparing it to like a published equation, we found that while the neural networks perform very similarly, the advantage of the published equation is that the coefficients are very easy to interpret, whereas, you know, the weights that you get from a neural network are very hard to interpret.
Yes, friend. Oh, go ahead.
So there's things you could do to pick the right models. There's AutoML, there's grid search, there's neural network architecture search, where you could decide what kind of architecture is best suited for your inputs and your outputs. So there's a different approach that you do, which are much more easily done with Python than Python.
Okay. All right. Okay. All right, so some takeaways for myself going through this project. I think that there's lots of different options that's out there, but obviously, for me personally, I want to go with something that's simple to work through, and neural networks is not. Neural networks is good, and it could be used, and it's not a problem. But you just have to be mindful about your parameters that you're setting, and it's going to take some trial and error to get the model that you're satisfied with. That's my experience. Yes.
As far as I understand, I heard that like one consideration of Python versus R is that in Python you can process like very large data sets on like multiple machines, while at R you're kind of limited to a single box.
Well, you could use Spark and that could help that.
Distributed libraries like
okay.
Spark that could
Yeah.
distribute any of those across multiple.
Okay, sure.
Yeah. So, okay. If you don't have any questions, that's all I got. Thank you for.